Okay, so let's just start. Hello, everyone. Welcome to another episode of the Machine Learning Seminar at Vanderbilt. Today, we are very honored and excited to welcome Dr. Sharon Lee from UW-Madison. She received her PhD from Cornell in 2017, advised by Professor John Hopcroft. Subsequently, she was a postdoc scholar at Stanford. Her research focuses on algorithmic and theoretical foundations of learning in the open world environment. She has served as area chair for iClear, NeurIPS, ICML, and program chair for workshop on uncertainty and robustness in deep learning. Um, and her work is recognized by at the NSF Career Award, MIT Technology Review, and various industry companies like Google, Meta, and Amazon. Her work is also received the NeurIPS Outstanding Paper Award and an iClear Outstanding Paper Award honorable mention in 2022. Dr. Lee, we are very excited to have you here today. Please take it away.
Thank you so much for that very kind introduction. And welcome everyone to this seminar. I want to thank all the organizers for inviting me. It's really a great pleasure to be here and give a talk at the Vanderbilt Machine Learning Seminar. Today, I want to share with all of you some interesting research challenges and progress that has been made in this exciting field of out-of-distribution detection. And during the talk, at any point, feel free to interrupt and ask questions. That's something I highly encourage. So let's get started. I want to start the talk by showing you this video. This is a perception model trained on a self-driving data set, which is performing bounding box tracking on the road in real time. And despite these, all the great performance like this demo has shown, the reliability of our machine learning models can often be challenged when we deploy them into the real world. And so in my research, I would really like to encourage researchers and practitioners to be more cautious of these methods and technologies that we build, especially pay attention to those unexpected or unknown situations that the model wasn't trained for. So to give you a concrete example, this was a joint project with my PhD student, Shufeng. And in this research project, we took this image from a data set called MS COCO, which is completely separate from the autonomous driving data set, right? And then we run through this self-driving car model that was just trained on this Berkeley Deep Drive data set. And so concerningly, you can see that the model would produce overconfident predictions for this unknown object, which is this helicopter in the middle to be as a truck. And keep in mind that this helicopter was never exposed to the model during training time. So in other words, deep neural networks do not necessarily know what they don't know. And this has raised significant concerns on models' safety and reliability. As you can imagine, algorithms that blindly classify these what we call out-of-distribution samples into one of the irrelevant categories can be catastrophic. And ideally, in this particular situation, what we really want the model to do is to say something like, I don't know, I'd rather abstain from making a prediction so that human can intervene and take more precautions. And this kind of example can translate and have a consequence in our real life. And for example, I'm quoting this news article from last year, which reported that a Tesla vehicle crashed into this private jet. And I'm sure you have seen some similar news in the past, right? And so what's happening in this video is this white car is driving toward this blue jet. And as soon as it hits this blue jet, it starts kind of spinning around. Unfortunately, no one got injured in this incident, but you can imagine the gravity of incident like this in some other scenarios. So this out of distribution detection problem has become very, very important. And this is going to be the focus of my talk today. So what is out of distribution data? You might be wondering. And let me first provide a simple view and definition on this. Let's say we have our training data distribution. In this case, it's a mixture of two Gaussians, right? For class label y equals to 1 and y equals to -1. They're colored differently in green and blue, respectively. And our in-distribution data would be the marginal of this joint distribution defined over the input space. In other words, it's what this green contour highlights. And in testing time, these orange dots would emerge, which are out of distribution from an unknown class, right? That doesn't belong to y equals to 1 or -1, and therefore should not be predicted by this model. So in other words, these orange dots really can be considered as type of semantic shifted out of distribution data here. And so that was a simple 2D scenario, and we can translate this toy data into higher dimensional data, something more complex like natural images. And so, for example, on the left-hand side, we have images from a data set called Cipher10, which consists of these common categories like truck, frog, horse, cats, and dogs, and so on. And on the right-hand side is a different data set called Street View Housing Number, or SVHN, which obviously have disjoint semantics from the left-hand side. Well, looking at this slide, I know you might be thinking this notion of OOD is way too obvious to human eyes, right? To us, but it turns out it's actually non-trivial for neural networks to differentiate these two types of data. And in fact, when the field kind of started tackling some of these problems, some of the earliest algorithms are achieving an error rate as high as 50% on this task, right? Meaning 50% of the OOD cannot be successfully detected. So it was challenging. And so SVHN is one possible type of OOD that model would encounter in the wild. And if you think about this complex manifold of natural images, there would be many other unknowns, as highlighted on the right side of this slide, right? So you can think of this as the manifold of all the possible images one can generate and encounter on the internet. And that's in sharp contrast to the left-hand side, right? That's the task-specific data set that our model was trained on, right? And so the right-hand side is really what the model needs to be deal with once it's deployed. And so out of distribution detection is, like I said, it's a pretty hard problem. And I want to just use a few slides to explain to you what the challenges are before we get into the solutions, how we solve this problem. So the first challenge is the lack of supervision from unknowns during the training time. Typically, our models are optimized using this training data, or we call in-distribution data. In this case, the green and blue dots, right, using empirical risk minimization. So we want to just minimize the overall errors made on this in-distribution data. And you can anticipate where these orange dots would emerge in advance, because there can be a huge space of unknowns that could emerge, right? What I'm plotting here is just a 2D space. But if you think about higher dimensional space, things become exponentially more complex, right? And this problem is further exacerbated by these high capacity neural networks that we're working with nowadays, which have this amazing fitting power, right, to achieve, near perfect classification accuracy on a task given. However, these models can produce problematic decision boundary when it comes to OOD detection. So to explain what I mean, let me show you this one of my favorite toy examples to illustrate this idea. So let's consider a classification task. It's a three-way classification task where our data is a mixture of 3 Gaussians, right? So there's class 1, 2, 3 here. And it turns out you can train a very simple neural networks, a multi-layer perceptron. It doesn't even have to be, fancy convolutional neural networks or transformers. And with multi-layer perceptron, you can achieve near 100% classification accuracy on this task. And this is what the decision boundary looks like. So what the model ends up learning is this triangular shape of decision boundary, where any points that's roughly above this on this upper part of this of this boundary is considered as class 3, and similarly, right, for the other 2 classes. And so this is all good if our goal is just to separate points arising from these 3 Gaussian distributions. But if you look at those red regions, that's where things go wrong for OOD detection, because those points corresponds to out of distribution data that could be deviating quite substantially from these 3 gray clusters. But nonetheless, model is producing a high confidence output. So in this case, model can't really distinguish very effectively what's ID versus what's OOD. Right, so that's the challenge here. And one last challenge I want to mention is that real-world images are often composed of numerous objects and components, like this complex scene I'm showing here. And therefore, we need finer-grained notion of OOD at this object level beyond image level. So over the years, we have seen this surge of interest in this challenging problem space. And here's kind of a summary of the thriving literature on OOD detection. So this is a really nice survey that's put together by my collaborators, led by Jin Kang. And if you're interested, this really covers quite comprehensively the methodologies developed in this space. And so in this talk, I'll try to unpack some of the interesting and important ones. So let's start with a method overview. How do we define this problem? So here, a model is, like I said, trained typically on the in-distribution data. So in this case, let's consider Cypher 10 as a running example here, right? We're going to optimize this neural network using empirical risk minimization, right? That's minimizing this average loss here on our training sample population. And once the model is trained, let's take this network as it is without modifying its parameters, right? Just imagine the model is going to be deployed somewhere and starts receiving test samples. And so this test input could be anything, right? It could be either ID or OOD. And so during inference time for any given input, our goal is really to devise this scoring function S, right, for OOD detection. So think about this scoring function being partitioning all of our data points in the space into two parts. If it's above this threshold lambda, we're going to consider it to be in distribution and produce the classification label as usual. And otherwise, we're going to reject this input for further examination, right? We're going to flag this. So it's essentially performing a level set estimation problem in this case. And the advantage of this kind of problem setup, which we call post-hoc OOD detection, is that it doesn't interfere with the models that are already being deployed or running in production, for example. And so in this case, the model is guaranteed to have the same classification performance while having this additional safety layer, right? Safety net for free. And I also want to mention that the problem is different from anomaly detection, which I'm sure a lot of you have heard about, which is a very classic problem in machine learning. But the key difference is that anomaly detection often treats all the data points as one class without necessarily differentiating the class labels, whereas here the goal are twofold, right? We're interested in this supervised task of classification and simultaneously doing OOD detection. So a key part of OOD detection is really how we define these scoring function, right? This S function, which I haven't really explained to you yet. So this question has driven a very rich line of works over the years, including our own. And for example, one of the common baseline is to use this softmax confidence score, which is defined to be the largest posterior probability, right? The largest P of Y conditioned on this input X. So the definition of the S function is given in this slide here. However, if we zoom into this area highlighted in this red circle, and so what I'm plotting here is really the distribution of the maximum softmax probability, right, across many samples of ID data, in this case, cipher 10, as well as a large collection of OOD samples from SVHN. And so you can see that the scoring function cannot effectively distinguish between these two types of data, or there's a highly overlapping area, right? That's shown in this figure here. And therefore, you can't draw a threshold somewhere to separate these two types of data easily. And this phenomenon is related to the fact that neural networks produce overconfident predictions. And later on in this talk, I'll explain more why softmax score is suboptimal for OOD detection. So fast forward a few years, in 2020, we put forward this energy-based OOD detection framework, which has the core idea that really influenced many of our recent works and other researchers as well. And so compared to the softmax confidence score, we showed that energy is much better suited for OOD detection. And so here is a high-level view here. So we still have this input, right, X that's going through this neural network, parameterized by theta. And then from this output of this neural network, we'll calculate this so-called energy function, which I'll talk about the definition in the next few slides. And then with this energy function calculated, we can perform this similar thresholding mechanism, right? And I just want to kind of point out here on the x-axis, we flip the sign of energy to be the negative one, just so to align with the convention that larger score indicates more IDness and vice versa. So this is a slight nuance, just to keep in mind that usually lower energy indicates more IDness, right? And so when we flip the sign, it kind of goes on to the right side. All right, so now let's dive a bit more into the details here. How do we define this scoring function? So energy-based model was first introduced to machine learning in the 80s and has been around for decades. And to give you some background, the energy function would take an input x, let's say my cat, and then the corresponding label y, and then it would produce a scalar called energy, right? It's a real value here. And you can think of this energy being measuring the compatibility between an x and y, and it should give a lower value if it's compatible in this case. And this function can be non-probabilistic, and if you want to turn it into a probability density, you can do so using the Gibbs distribution, which would normalize among all these y states. And so again, this is the same equation in the previous slide. If we look at this denominator, which is also known as the partition function, it's taking the integral over all the possible y's, and by equalizing these two sides, we can see that free energy can be expressed in terms of the negative of the log of this partition function, right? And so far, everything has been around for a long time in physics. And so how is this related to this, modern neural networks and moreover OOD detection? So it turns out that a neural classifier can be interpreted from an energy-based perspective. So now let's, consider a neural network, in this case, producing output logits F1, F2, and so on, right? So these are pre-softmax output. And then we can apply the softmax function, which normalize across, all these outputs and give us normalized probability P of Y condition on X. And this is the definition we've seen before. And so now if we define this energy function E of X comma Y to be the negative of the logit, effectively this turns into something that we just saw earlier, right? So you can see this symmetry here between this softmax definition of this and this energy-based definition here. So recall this is how free energy was, defined in the previous context. Now for a neural network, multi-layer classification network, this free energy essentially replaces the integral with the summation across k discrete classes. So now for every input x and a neural network output f, we can calculate this very conveniently using the log sum exponential operation here. So this is the definition that we'll be using quite extensively for the rest of this talk. So with energy score, we show that the distributions between ID versus OOD becomes much more separable. So far I've introduced two scoring functions now. So it probably makes sense for us to kind of look them together and contrast them a little bit more. So this equation on the upper side is the posterior probability, right? And that's where softmax confidence score is derived from, which is the maximum among all this P of Y condition on X. And the energy function is defined at the bottom of the slide, where if you look at this connection, right, it's really the negative log of the denominator in our softmax function, right? So that's kind of the green box that I'm trying to highlight here. And interestingly, if we rewrite this posterior probability to be the joint probability divided by the likelihood, right? You see that the energy score has an inherent connection to this negative log likelihood. or a negative log of P of X. And so that's one step closer to what we truly desire for the purpose of OOD detection, right? But it's not quite identical in this case, but we'll come back to this aspect later. But the point I want to make here is, we really shouldn't be utilizing this posterior probability, P of Y condition X, for the purpose of OOD detection. And I won't go into the details here, but in the paper, we also showed that minimizing this cross entropy loss has this effect of pushing down the energy score for ID data. So that's why during the course of training, we can prove that by analyzing this gradient of the loss, these energy values for our training data distribution kept to be lower. And so now if we look at the softmax score, or more precisely, the log of the softmax score, we can decompose that into two terms. So here, the energy of this input plus the maximum output. And keep in mind, the first term, right, as we explained, is going to be decreasing over the course of training. So E of X is going to be lower for our in-distribution data. And the second term is going to be higher, right, in order to minimize this cross-entropy loss. And so this overall summation actually results in a biased function that's no longer suitable for OOD detection. So we can evaluate these two scoring functions and compare them side by side. So empirically, we train a neural network on the Cypher-10 data set and evaluated against SVHN as OOD. So this figure on the left-hand side shows the performance using softmax score. So we're measuring the performance in terms of FPR 95, which is defined as follows, right? So essentially, we're choosing this threshold based on the purple distribution here, because in distribution is all we have, right? And so we're going to choose the threshold. Let's say where 95% of our in distribution is above this threshold. And then we're going to use this threshold to test and see what's the fraction of the gray distribution that's misclassified as ID. And the lower FPR is better. So in this case, we're observing roughly 49% of FPR. And in contrast, when we switch this scoring function, we see this improvement in terms of FPR, right? It's, in this case, it's reduced to 35%, which is quite significant. And in the paper, we showed the comparison on a wider range of out-of-distribution test data sets. So all the blue bars are based on the softmax score, and the green bars are based on energy score. So there is a consistent improvement here. So far, I have talked quite a bit about scoring function, but in my view, I think they're only part of this solution. And in order to mitigate these problems more fundamentally, we have to kind of move beyond these post-hoc scoring function design and really rethink how we design the learning objective of our machine learning models during a training time. So to explain what I mean, let's revisit this example, right? And so here it's a model trained using the standard cross entropy loss, and the decision boundary is problematic, right? It's insufficient for OOD detection purposes. And the reason it happens is because our existing learning objectives are primarily incentivized by optimizing accuracy only on the in-distribution task, right? And they don't account for these uncertainty that could arise from outside the ID data. And so going beyond this standard learning objective. What we really need is this training time regularization that can explicitly account for uncertainty outside the ID data. So the ideal decision boundary should be something like the right-hand side that's more aligned with our underlying data distribution, right? And so the question is really, how do we go from the left-hand side to the right-hand side without having to perform this density estimation, because that's a highly intractable problem in high-dimensional space, right? So to do so, one promising learning paradigm that we put forward is this notion of safety-aware learning. So you can think of this as a combination of two objectives. One that's still minimizing this classification error on our ID data. And in addition, we have this second term that's trying to separate ID versus OOD, right? In some sense, it can be viewed as an uncertainty regularization term. So the overall objective is saying, not only I want to be able to distinguish among my in-distribution classes, but at the same time, I want to have this capability of separating ID versus something else, everything else, right? And so that's what this objective is trying to promote here. And now let's zoom into the second term, which is more interesting here. So how do we define this mathematically? So for now, let's assume we have some access to, the auxiliary outlier training data. And so our idea is to explicitly push the energy score, which I'm putting this definition here on the right side. And so we want to push this energy score to be as separable as possible between these two types of data. One is ID on the right-hand side, and the gray is OOD. And this objective has some nice mathematical interpretation too. Essentially, we're performing this level set estimation based on this measurement. And this measurement is related to this notion of negative log likelihood. But it's, in fact, a much simpler objective to optimize than performing density estimation. So essentially, we're saying, it's suffice to have a measurement that can separate ID versus OOD data without having to get this P of X exactly for every single distribution point, right? So that's the subtle difference here. And so the result of this training is more separable distributions measured by the energy score. So you can see the rightmost plot here, where the FPR can be further reduced to 1%, right? So that's significant reduction compared to if you take the model trained with cross entropy loss. And so this is a promising framework, but there is one caveat, which is, in order to optimize for this objective, we do need some auxiliary outlier training data. And so the question is, where do we even get those data from? In practice, collecting those large outlier data can be arguably very expensive, right? Because we need to perform this careful data cleaning to make sure that our ID data and whatever outlier data we're using for training do not overlap. And this process needs to be repeated every single time our ID data changes to be something else. So it's not very flexible. And that motivated us to ask the question, is there any way we can generate OOD training data automatically for free? And we answered this question as part of our previous paper shown here called virtual outlier census. So the idea really is, provided with just ID training data, can we generate these outliers from the ID data, right? So the key idea in this paper is to synthesize outliers in this low likelihood region of the feature space, and then utilize them for model regularization. And synthesizing in a feature space has the peeling kind of property because it has much lower dimensionality compared to synthesizing higher dimensional images in the pixel space. And this suits our purpose well because we really care about regularizing models' decision boundary. So here's how it works in a nutshell. You can think of this purple box being the feature space, say the penultimate layer of a neural network, right? The one layer before the final output. And in this case, we model the penultimate layer as a class conditional multivariant Gaussian distribution. And so you can estimate this mean and covariance matrix based on the empirical samples. And so once it's estimated, then we can start sampling from these distribution, right? And then preserve the points that have relatively low likelihood, as shown in this dark brown points here. And you can do this for every single class in our training data. For example, this 3 clusters corresponds to different classes in the embedding space. And the dark points are the synthesized outliers in the feature space, right? And so once these dark square points or all these, virtual outliers are generated, then we can pass them through the fully connected layer. Remember, this is the space they're generated, right? That's the purple box highlights. And we can calculate the output through this linear transformation. And that W matrix is really the classification weights, right? Connecting penultimate layer to the output. And this is shared with our, the network that we're using to train the in-distribution data as well. And with this output, accordingly, we can calculate this energy score, right? That turns all these F output into a single scalar. So putting everything together, this is the overall formulation of our learning framework. So it's jointly optimized for the classification error, which can be cross entropy loss. And the second term is pushing the energy score to be apart between the ID data sampled from this distribution D and the virtual outlier distribution, right? That's synthesized using the procedure we just described here. So I also want to mention that LOS is a quite general learning framework. In the paper, we showed that it's actually working not just for image classification, but you can also use this for object detection. In this case, we just add one more loss, which is localizing these bounding boxes here. But the underlying fundamental idea still remains very similar.
I have a question,
yes.
if I may, in this previous slide. So when you generate these virtual outliers, if I understood this correctly, you're generating it per class, right? So we assume that every class, the penultimate layer of the network, the features for every class are distributed as a Gaussian. And then you generate something that's, let's say, 3 standard deviation away or 2 standard deviation away, right? So how do you ensure that those generated virtual features are not coming from other classes? Still in distribution from other classes?
Still in distribution from other classes?
Right, so class yellow in the middle, for example, right now we go and we generate these outliers, but those outliers for this class specifically could be images from another class, right?
Yeah, that could be a potential concern. So the way I would say, to kind of rule out this situation, there are several considerations when, realizing this idea. One is, we could try to add this regularization to make sure that each class conditional Gaussian distribution is distributed as far apart possible, right, apart from each other. And so that ensures at least the yellow cluster and the green cluster are not really close in this embedding space. And this actually can be done using this prototype-based optimization idea. I didn't talk about in this work, but there are, mechanisms that allows us to do so. And then from the sampling side, I think it's very important to kind of to select this, like the threshold very properly, because, like you said, 1 standard deviation, 2 standard deviation would induce outliers that are, different distances away. And what we really want here are the virtual outliers that lie closely on this boundary of our ID data. And that has the strongest effect in terms of generating the decision boundary that's conservative or more compactly surrounding our ID data. And so that's one thing to be intentional about here. So we don't want to go too far, because if it goes, likelihood goes extremely low, that means it's already deviating from ID data too far, and it learns the decision boundary to be too loose. I think you're muted, Sohail.
Sorry, thank you. Yes, that makes sense. Also, there is another question from Professor Lane. Forrest, can you ask the question yourself?
Oh, okay. Sorry, I wasn't able to track the chat thread. Maybe I missed that question.
No worries. So I can ask the question. Won't the null space for the penultimate layer, linear layer, be very high dimensional? Which would mean outliers, large m distance in penultimate feature space, lying in this null space be impossible to distinguish as high energy. Forrest, you're allowed to ask the question. I think if you unmute, you can ask the question yourself or comment on the question.
Yeah, I'm not sure if Forrest is on the line here.
Yes.
So let me I think he's
sorry about that. So I was in a loud space. I had to come out somewhere quiet so I could speak.
Sure.
Yeah, I'm sorry. I was just saying, because so here it looks like you're kind of classifying outliers, these virtual outliers, as having a large distance from the average feature values, right, at this penultimate layer. But then these things pass through this final linear layer. And maybe I'm wrong, but usually wouldn't it be that like the penultimate layer has a much higher dimension than the final output dimension, which means that there's probably like a very large null space, meaning like a huge space of feature values at this penultimate layer that all project down to the exact same ultimate feature output classes. And so therefore, like, you could start in the at the final layer and like compute the pre-image of all penultimate features that have the exact same energy. And those could all still be definite outliers in the penultimate feature space. Does that make sense? I'm just wondering if you find like thought about that and if that impacts the ability for this to work to capture these outliers.
So you're right that the penultimate layer could have a higher dimensionality than the output, right? So that means it's possible after the projection, even though the virtual outliers in the original penultimate layer lies in a different spot, they could be projected still down to very, very similar points in the output space. But recall that our ultimate goal is to then further reduce this output into a single scalar, because all we care about is deriving these scoring function, right? To train these energy surface to be separable between the ID versus OOD data. So as long as that level set is learned effectively, we could still basically achieve our goal here, even though they may be projected down to similar points after this transformation.
Great. Yeah, thank you.
And I'm happy to, follow up after the talk to elaborate more on this.
Thank you.
Thank you for that question. So in the interest of time, let me maybe try to finish the remainder few slides, and I'll, open up to more questions and follow up more. So I want to give you some kind of concrete visual evidence here in terms of how this framework can help. So recall this is the, at the earlier on of this talk, we showed without VOS, if you just take a object detection network in its vanilla form and train it, it has this, safety issues. And on the right-hand side is when we train with VOS, it can successfully flag some of these unknown objects. And here's one more example where the stormtrooper is flagged as OOD for self-driving model. This is just for kind of a fun visualization purpose. And I do want to point out that one limitation when we work on this original VOS framework is that it makes a strong distributional assumption about the feature embedding space, where you could easily question, well, the neural network may not converge to or learn these Gaussian distributed feature representation space, right? And so we mitigate this problem in a follow-up work called non-parametric outlier census, or NPOS. And I won't be able to go into the details here, but just at a high level, this framework is introducing a new sampling mechanism in this non-parametric manner. This way, we kind of get away with making distributional assumption about the feature embedding. And so it can work with embedding of any geometry and offers stronger generality and flexibility. So you can, you're welcome to check out the work if you're interested. And one more cool follow-up that we did after the original VOS is to kind of wonder, what we're really losing there is, we don't really know what these virtual outliers looks like, because we kind of, push things into the feature representation space, which makes the scene size more tractable. But what we lose there is interpretability. And so recently, there is an upcoming Univeristy paper that we kind of try to make sense of these synthesized embeddings by projecting them back to this high-dimensional pixel space. And these are some cool visualizations. We see, for example, these are the outliers synthesized with respect to strawberry in this case, right? These are big strawberry leaves next to the farmhouse. And this is another kind of, outliers synthesized with respect to strawberry. So these are really kind of cool visualizations. We have a lot more in the paper. And so it's a kind of an interesting framework that mitigated some of the interpretability side of issue, if you're interested in finding out more. I think I'm running out of time. How much time do I have? I can skip some of those final few slides if.
We have 7 minutes till the official end of the seminar, but if you don't have a time constraint, I think like you can go on, and we can violate the time a little bit.
Sure. How about I try to wrap up in 3 minutes? This is really just a very few slides. So again, going back to this challenge of where do we obtain these auxiliary outlier data, right? So synthesizing outliers can be one route, but you might also be wondering, what if we don't want to synthesize? What if we want to obtain these natural outliers, right, that are occurring in the real world? How do we get those for free? I think there's very interesting opportunities in terms of leveraging wild unlabeled data for OOD detection. So what do I mean by wild data is really, let's say you train a self-driving car model and then you deploy this into the wild, right? And as the car drives on the road, it's going to receive all kinds of data points that are either ID or OOD in all kinds of road conditions as well. And so that's what we call wild data. And so in other words, it's really the data that's naturally occurring from the model's deployment or operating environment. And so here are several advantages, as you see, in terms of utilizing wild data, because they're easy to collect, and you don't need to go through heavy annotation, and it often represents a much better match to the true test time distribution, because we know that part of the OOD would be, in this wild data already, right? But the challenge is also quite severe. Is one of the key challenges that the data is heterogeneous, which means they consist of both ID and OOD data at the same time, right? And because every data point is unlabeled, so we don't really know which one is ID, which one is OOD. And so mathematically, this can be characterized as this mixture distribution here. P wild is a combination of the marginal distribution P in and the marginal distribution of P out with some mixing ratio pi here. And so the interesting research problem really is, well, provided with a cleanly labeled ID data, and together with a large collection of, wild data, that's a mixture of ID and OOD, how do we leverage these two sets, right, to train a reliable classifier and the OOD detector jointly? So I won't go into the technical solution here, but I do really want to point out this interesting direction. If you're interested, these are a couple papers that we have published recently along this direction. I would say, there's still a lot more can be done on the algorithmic solution side, right, to really make use of the wild data. Lastly, let me just conclude today's talk. I hope this talk has really helped you understand better about the challenges that we face in the space of out of distribution detection. And some of the early work tries to tackle the problem using this post-hoc approach, right? Developing scoring functions that can effectively distinguish ID versus OOD. And there is a fundamental limit in terms of how well you can do using the post-hoc approach. And very importantly, the key message I want to share in this talk is that we need to rethink how we design our learning objective by explicitly account for these uncertainty during the training time. And so this way we can learn a much more compact and safety-aware safety-aware decision boundary, like the right-hand side of this figure here, that not only help us separate ID classes, but at the same time have a much stronger OOD detection capability. So with that, I want to thank you all for being here and attending this talk today. And I'm happy to take more questions if there are any. Thank you.
Thank you so much. Fantastic talk. I really enjoyed it. Now it's open for questions. Everyone, please post your questions. I think there is a question from you. Based on the heat map figure showing that the classification boundary becomes really closer toward the training samples after applying the training regularization, have you observed that the training time regularization would potentially hurt the model generalizability in the experiments? If so, how do we control the trade-off between these two?
That's an excellent question. Thank you for raising that. So let's come back to this figure here. So it's very important to kind of control during this regularization. I think a key factor is to make sure that the synthesized outliers do not kind of go too excessively towards shrinking that in distribution decision boundary. And so there's a careful kind of balance needs to be made there. And in practice, what we showed that is depending on the regularization strengths and also the sampling hyperparameter, right? You can control these various factors. And when these are controlled properly, you can actually achieve almost similar classification performance or object detection MAP while having significantly better OOD detection performance. So it's very possible to have good word of both without necessarily sacrificing the ID data performance.
Fantastic, that helps. I think Brian Liu. Brian, you're allowed to ask your question.
Hi, Professor Lee. Thanks for the talk. I have a quick question. The first one is I wonder if training with an unknown class, which is unlabeled data, just label them as unknown will achieve the same effect as OD detection. So let's say you have, 10 class classification problem, right? And then I'm pretty sure there are other classes other than these 10 classes. How about we just, let's say you're working with CIFAR 10, then we have, a bunch of data from ImageNet, outside these 10 classes and label them as, unknown. And I wonder if this, has basically with these unknown classes, you train on CIFAR 10, you test on, let's say another data set, MNIST, for example. And I would expect, the model would be able to output, this is that unknown class.
Yeah, thank you for that question. I think what you're suggesting is actually a very well-known baseline called outlier exposure. This is something the field has indeed explored in the past, right? What if we just take an auxiliary? So what, early on, I mentioned this notion of auxiliary outlier data set. So for example, this the result of this figure is really based on something similar to what you just described, right? Let's just take additional data set that's outside the ID data set. And it's quite effective, but there are a few caveats and limitations to note, right? One of the limitations from a practical perspective is that you do have to go through this manual data collection, right? And to ensure this auxiliary data doesn't overlap with your ID data. And this needs to be done very, very carefully, and it's to be repeated for every ID data. And so that's one caveat that kind of motivated us to think, can we somehow get rid of this, reliance on these auxiliary data set, right? Because in practice, if your learning algorithm only requires ID data, that is much more appealing compared to the algorithms that has to rely on additional carefully curated sets. So that's one point. And on the OOD performance side, I also want to note that, there is a potential OOD in terms of generalization gap from an OOD detection perspective. Say if we're utilizing auxiliary outlier data that's sampled from, a potential P out distribution, and we're evaluating on something, your test time OOD distribution could be something different, right? And so that would result in suboptimal performance in terms of OOD detection when you train on one auxiliary data distribution and test on the other. And these drawback can be mitigated using, this is what I kind of hinted in the last part of the talk, is to say, if you actually train on something that matches better with your test time OOD distribution, you have much stronger guarantee there. Right. Yeah. That's the trade-off there.
I see. Okay. Actually, I have a follow-up question. Maybe I can let others ask
Brian,
first.
I'm so sorry to interrupt. There are 5 questions in the question and answer. So maybe we can take your future questions offline. Let's go through the questions, and we're already over time. Tyler, you have a question?
Yeah, thanks for the talk. So I had somewhat of a follow-up question, I guess, on both Sohail's comment questions and Yu's comments and questions. So how, I guess, how reliant of this synthetic OOD generation and the detection on the classification performance? So I guess part of the assumption is that, like Sohail was mentioning, of if what's generated as a synthetic OOD is in distribution for another class, is that we're able to separate the classes. But I guess on some of these benchmark image data sets, the classification performance is generally very high. And so if this were to be on a data set that classification isn't quite as good, how coupled this performance is for the OOD detection?
Thank you, Tyler. That's an excellent point you're raising. I would say, yes, this ID classification performance, or how well these ID feature space can be learned, would indeed have an impact on the synthesize capability. Because after all, these key the key sampling component relies on how well we can, for example, right, approximate this density in this feature space. And this relies on really a well-learned feature representation to begin with. And this capability varies from different ID data set. For example, on Cypher-10, you can achieve this much more easily as opposed to much larger complex data sets such as ImageNet. And there, the scalability and complexity of the sampling also increases too, which can have an impact on the performance. And I also think another aspect that ID, the ID data or accuracy could have an impact is this notion when we're dealing with a low resource ID data, meaning when we don't have ample, a large collection of samples from ID data, this could also manifest, right, in terms of how well we learn these embedding and how well we sample. So all these could cause disparate performance.
Thank you.
Yeah, thank you. That's a really, really good point.
Sharon, I know that we are way past the time, but there are some really good questions. Do you have time to answer maybe a few more?
I do. I actually, my 101, I have a student meeting, doesn't start until 1:45. I'm happy to just, finish answering all those questions.
Fantastic. So Forrest has another great question here for us. I'm going to rephrase it essentially. And how do we do near OOD detection versus far OOD detection, right? It's like CFAR10 versus SVHN, like that may be considered far OOD, while CFAR10 versus CFAR100 is near OOD. Like, where do we draw the line? And since we have done a lot of work in this area, like, do we have good benchmarks that actually tell us what problems are near OOD, what problems are far OOD?
Yeah, thank you for raising that. There's definitely, I think the recent trend in the OOD detection community is recognizing, right, there is this characterization of far OOD versus near OOD, and they really come at different intrinsic difficulty, right, for the detector to work well. But one of the kind of core, I think what's shared in between these two detection problem is that regardless of whether you're dealing with far OOD or near OOD, it will be effective as long as you're learning a decision boundary that's compactly surrounding our ID data, right? Because imagine in the right side of this figure, think of this as 3 out of Cypher-10 classes. And if you can capture this kind of decision boundary tightly surrounding your 3 in distribution classes, you're able to effectively distinguish far OOD for sure, right? Because those are the, in the deep dark blue region. And those near OOD would be somewhere, maybe in between the blue and gray, right? And so those would translate into kind of, slightly harder cases to be detected. And so in that case, the tighter we have this estimation on the decision boundary, the better we can identify the near OOD. So that would be, how I would think about this issue.
Right. Fantastic. And so there is a question about OOD problem. How do you view OOD problem in the era of large language models? Like, have you looked into quantifying OODs for these LLMs?
Fantastic question. Yes, indeed. I would say, the work is right now we're barely scratching the surface, but we do have some initial attempts in terms of understanding OOD in the context of language modeling in general. I do want to point out one of the ACL paper that was just published a few months back. There we were looking at these distance-based approach for identifying out-of-domain samples with respect to these training domains. So if you're interested, definitely check out some of the works there. We also have some recent effort in terms of looking at out-of-distribution detection problem for multimodal, multimodal in general that combines vision and language information jointly. For example, how do we define this in the context of CLIP, right? There has been some work down there as well. So definitely, check out those works. Unfortunately, I didn't have the time to cover those. Maybe sometime in the future.
Great. There is a question that I'm not sure if I understand from Amir Hossein. Can we consider RL-based training instead of safety objective to have better performance rather than regularization for OOD detection?
I guess maybe it would help to understand better what you mean by this RL-based training.
So, Amir Hossein, if you elaborate on your question, we can revisit it. There is another question about leveraging uncertainty to build post-hoc OOD detectors. There are many uncertainty quantization approaches, right? Like the Bayesian approaches, like Monte Carlo dropout and so on. So how do they fare in out-of-distribution detection?
That's a really good point. My personal opinion is that these uncertainty-based approach are, not fundamentally going to solve these out-of-distribution uncertainty, right? To give you an example, like if you take ensemble-based uncertainty estimation as one of the, prominent approach there, essentially what you're doing is to take, multiple neural networks, right? Each trained with different initialization. And then during test time, you wanted to kind of, average, look at across the average prediction to have some uncertainty-based notion. But why is that insufficient? It's essentially, if you look at the left side of this image here, right? Every model is learning this ill-fated or problematic decision boundary. And an assembling-based approach is really just aggregating 10 or multiple these problematic decision boundary, right? So at the end, you're still dealing with maybe slightly better than this individual decision boundary, but still somewhat ill-fated. And so essentially that's not going to be as direct as if we were to incentivize this network to learn something on the right-hand side.
That's fantastic. Thank you. And last question, I promise this is the last question, again from
Sure.
Brian. But the question is about there seems to be a trade-off between how well we can detect out of distribution and how well our model generalize to near OOD data. So if we want to train a network that generalizes to near OOD data, then we shouldn't be able to detect out of distribution. Is that correct?
let me think about this. So you're saying in case of near OOD, overly tightening the decision boundary would hurt the generalization of ID data, or would hurt which part of the performance?
Yeah, so I believe when we are talking about generalization here, we need to be careful, right? And this is not my question, I'm just speculating here, right? So CFAR 10, for example, let's say we have different classes of vehicles. On CFAR 100, we have different classes of vehicles. On CFAR 10, we have only one or a few of them. So if we say from CFAR 100, we are still classifying trucks, which did not exist in our CFAR 10, as cars or as vehicles. Is this a good thing or is it a bad thing? Because we have never seen truck, but we have seen some things, the things that are similar to a truck in the past, and they were vehicles. And so if you're classifying those as vehicles, is this something to consider correct or incorrect? And if you're doing distribution detection, then maybe our model will say, I don't know what this is because I haven't seen it.
Yeah, that's a really great question, I think it depends on how you want to, it really depends on the learning goal here, right? If our goal is to say, I want to really strictly detect those despite, slight concept variation from a truck to, fire truck, I want to still detect those as out of distribution, then you want to learn as tight decision boundaries as possible. Whereas if your goal is to say, maybe I care more about generalization, right? Despite that slight shift, this fire truck still has, similar underlying semantics as one of my training categories, in which case maybe you don't want to over-regularize the neural network there. I think there is this is a slight kind of gray area-ish of a problem to be defined more clearly, right? And then you can kind of design these learning approaches so accordingly that's tailored to that. I don't think this aspect is as well studied in the field yet, and so that might be something to look into further. That could be an interesting research question.
Fantastic.
I like that.
Yeah, thank you so much, Sharon. This was a very informative talk. I really enjoyed it. Great question and answering session. And thank you so much for staying over time and answering all the questions. We really appreciate your time. And yeah, I mean, if everybody, can you unmute and we thank Sharon one more time. And
thank you for a great talk.
Thank you again for hosting me. I had a really great pleasure, and I appreciate all the wonderful questions here from the audience too. And in case you want to follow up on some of those, feel free to reach out to me. This is my email address. Yeah. Great. Thank you so much.
Thank you.
Have a good rest of the day, everyone.